trick of the MMU is that we then allocate the ones of these that we need most readily into RAM. So let's say this address space we definitely that chunk of address space we definitely have to have, and then these two definitely have to be there. So we'd allocate them into memory, and then let's say process 2 is also running. So we're switching between the two processes quickly. So they're both doing stuff live. So maybe you're listening to music and you're editing stuff in Word. And we definitely need all of these bits because they're being used. So we allocate those. What the MMU does is this bit. So all of these lines are in the MMU. Does that make sense? So the thing that tells us that this, when we ask for something in this bit of the virtual address space for process 1, we look in that bit of RAM. That's recorded in the MMU. So we're essentially saying process 1 is in slot number 1 in our RAM, and process 1 is also in 2, and process 1 is also in 3. And there's a little bit more involved than that. There's a bit of maths that goes on to do the translation between those. That's why you've got an actual CPU there. You've got an actual, sorry, not a whole CPU, but an actual processor doing something there. And we've also got process 2 in 4, 5 and 6. Then the final bit of the trick is that anything that isn't in there, so this one, this one, this one, this one, this one, this one, and this one are in the hard drive.
Is that very similar to the actual paging itself though? Because isn't that the effect of keeping the most recent stuff in main memory and the stuff that's the least used in the hard drive?
Well, the things are entirely linked. Virtual memory and paging, and the act of paging are all interlinked.
Okay, right.
Paging is part of the process of making this happen.
Because in the past paper, it's been split into like 2 questions, and it's hard to differentiate the answers.
So what was the next bit of the question?
Just get it out now.
So does anyone have any questions?
So it also references the memory locations within the hard drive, and it stores that in the MMU. Or it just says it's on the hard drive.
You don't need to know a lot of the detail about what's going in the hard drive. Essentially, it will keep a file on the hard drive that will store each of these bits of memory in a certain location.
Page file.
Yeah, in the page file. I guess you could have a file for each of these. It will also have somewhere in the operating systems, like global variables in its memory, an equivalent of this saying which file or which bit of the page file is storing each of these. Because at some point when it does paging, it will need to go and load the right one.
But it doesn't store that in the MMU. It only stores references into main memory in the MMU.
That's right, yeah.
Right.
So it doesn't tell, the MMU won't keep track of what's on the hard drive.
Nice.
It'll keep a separate set of memory.
Separate file for that.
But the MMU is purely about doing this mapping, because it needs to do that quickly, right? If it's already in real memory, it wants to get that information as quick as possible out of memory, because the CPU's trying to use it. It's trying to read a value that you've said is in this virtual address space, and if that is in real RAM, then it can grab that quickly, get on with doing the next bit of its process.
Okay.
Nice.
Okay, yeah,
That's good. Yeah, it makes a lot more sense now.
Yeah.
Okay.
So that question there, then, just to recap everyone, that question there answered this: what memory management technique is used by the memory management unit to run a process which has a memory requirement bigger than the available RAM? So that's how that's answered there. Okay.
But does that technique have like a specific name, like a
virtual memory?
That's virtual memory.
Virtual memory. Okay. So then the next question is: paging and segmentation are memory management techniques. Briefly explain each technique, including its purpose and benefits in the OS. So, aren't you already talking about paging in the previous question?
Yeah.
That's why we're getting.
Yes.
Wondering if they're separate or not separate.
Virtual memory and paging are conflated almost, but they are slightly different things. Virtual memory is this whole setup, describes the whole setup, and meaning that that you're doing this thing. Paging is the actual technique of when you have something missing. So when we try and access this one here, and we go, oh no, it's not listed in the MMU, we can't get it, it's on the hard drive, then you have to stop trying to do what that process is doing, because it doesn't have the thing in memory that it needs. And then it does this thing called paging, where it does the operating system then runs a different bit of code, which will go and find on the hard drive which bit the page file is in, copy it into one of these, so it'll probably copy it, let's say, into 6, and then it will allocate 6 onto there. And suddenly that becomes available, and it can...
And it'll store that reference in the MMU.
And then it will store that reference, yeah, correct. It will add one to here, so process 1 is in...
Ultimately, it just keeps a list of the references of where everything is.
So really, how in terms of answering that question, you've almost really answered it in the question before, haven't you?
Yeah. Sorry. Repeat what the question.
So the new question is: paging and segmentation are memory management techniques.
Yeah.
Briefly explain each technique, including its purpose and benefits in the OS.
Yeah.
So it's almost confusing, those two questions, because
they're very similar. Yeah,
that's what's confused us, because we try to answer the questions and then think, well, they wouldn't have asked you the same question twice, so they must be different, but they're not.
This is the reason it's worth reading ahead and trying to work out where you can get marks for different descriptions. So I think in that question you'd get marks for describing virtual memory, because what's the mark distribution in fact between those?
That question there is 8, and the question that I'm asking you now is 10.
Okay.
So the next one is more.
Interesting.
So this one also includes segmentation, doesn't it?
Segmentation.
Yeah. So I imagine for that there'd be a few marks for identifying that this is called virtual memory.
Yeah.
And then a diagram like this, like explaining that you're mapping on.
Even though it doesn't say diagram, can you do a diagram?
Always, yeah.
So even though it says explain, you would be happy with a diagram rather than...
As well as...
I'd expect a few words as well to explain what's going on in the diagram.
Okay.
I think having the diagram will help you explain what's going on better. Like having drawn it down and reminded yourself of what's going on here, you'll be able to remind yourself, oh yeah, there's address spaces over here, and they're linked to bits in the real memory, in the RAM, and it does that by using the MMU, and sometimes some of the bits go onto the hard disk.
Got it. Okay.
So yeah, I think describing that generally, like that there are these different things, so sort of surveying what all the components are would be what would explain virtual memory. Paging, I imagine if you explained what the process was, what happened when something isn't, when memory. Part of the virtual address space isn't in RAM. That's when you describe what paging is. And obviously you'd also get some marks for explaining what segmentation is. And I think it asks you what's different.
Yes, it says including its purpose and benefits in an OS.
Okay. Okay, so no, that's probably just 5 for each. You get 5 for explaining the two. And also it's asking for what the benefits of paging as well. So you sort of know that one is it allows you to have more things that are bigger than RAM, but it also allows you to have more processors than you'd fit in RAM, and it would also allow you to, and it does that quicker than swapping. So if you remember swapping, it's not having segments of
it's literally the whole chunk.
It's the whole chunk that you either put on the disk or put in the RAM.
For each process.
Yeah, for each process.
Okay. Yeah. So segmentation we can look up, can't we?
I think I don't waste more your
segmentation we can look up. I don't waste more of your time. But this question we're asking now is one that we've all struggled on loads. It says explain how the address space concept allows the OS to support multiple processors in main memory, giving at least one of the benefits of this concept.
Yeah, we didn't know
we were lost on that one.
Okay.
Address space concept. We tried looking it up and it was like,
So what do you know about an address space?
What you just told us, that address space is a linear block.
Okay.
Of main memory.
Yeah. Is it always main memory, isn't it? Is it always main memory?
It's always referring to main memory.
Right.
Where sometimes it's actually in main memory, depending if it's an older operating system. Sometimes it's like this. You're telling the process that it's in main memory, but actually, as you can see from here, over half of it isn't. Just some of it is. So the things we know about the address space are that it's a list of addresses that begin at some number and end at some number. So we'll start at 0 and we'll go up to, let's just pick 16. So we've got all these slots that we can put variable numbers in, and that might be that we're storing numbers because we're counting how many times around a loop we've gone, or we might be storing the number equivalent of letters because we might have stored a word in here that the user's typed in or something like that. All of those variables that you create in a Java program and things like that, they're things that go into your address space. You haven't really had to deal with this in Java because Java handles all of the memory allocation itself, but in lower level programs, and in fact the compiler does this for you when Java or the virtual machine does it, when it translates what you've done in Java into a piece of code that will run on your machine. It has to work out where to put things in some space. Now, if we're going to say that in our full RAM we're going to split that up amongst processes, and now this is going back to the level before virtual memory, because virtual memory confuses it that little stage further. If we're going to say how many are we going to fit in? 6 processes. Process 1. Our entire memory, let's say it's made up of blocks of this size of 16, so our entire memory would go from 0 to 16 to 32 to 48 to 64 to 80, is that right? Yeah, 80 to 96. If it's made up of little blocks of 16. This is a very small set of memory, but let's imagine that because the number is a little bit easier. When we put process 2 and its memory in this block here, in the real memory, so when we're referring to the variables and things like that, when we're running those instructions that are doing like mov some address location and into a register, so we've got a register that we're trying to copy something out of main memory onto the CPU so we can add one to it or something like that. The issue is that process 2 might not have been moved into this address space. So when you're writing the code, when you're creating the code or compiling the code, and it needs to know which memory addresses to refer to, if it always knew that it would be in this second slot, if it always knew that, oh, I'm the login program, I'm always going to be between 16 and 32, that'd be fine. You could write the code so that the first variable's in 16 and the second variable's in 17 and so on. Mm-hmm. The issue is that we want an operating system where we can load any of these processes in any order. You'll probably have this first process, which is probably your kernel program, which is running your whole operating system. But then the rest of them, you want to be able to be, well, what does the user run? The first thing the user launches when they launch their operating system is your word processor or your browser or something like that. But the other time they run it, they might be launched in a different order. They might only open the browser, and then the third thing is the MP3 player or something like that. Yeah. So the processes might come in different orders. And that means the code in those can't be written to make use of exact values in the memory space, can it? Because if we loaded Word in the browser, if we'd written the code so that it worked exactly like that, if we loaded the browser separately up here, if the browser thought it was in here, it would be referencing memory addresses that are saved for a different process. Yeah. So not only would the browser not work, but it would also be interfering with another process's memory. So, the idea of an address space is that you pretend to the process that it has 0 to 16 in this example. Obviously they have different size processes in a real operating system. But we pretend to each of them that they've got this first slot. They've always got 0 to 16, for instance. And that means no matter where they go, the code for it, the instruction set, the instructions for this process, will always refer to a variable that's somewhere between 0 and 16. So let's say 0 to 0. Then there's a trick that the operating system has to do to make sure it's actually referencing the right place in here, regardless of the fact that it's asking for 0. Can anyone remember what that is? No? Okay, so do you remember the range and the limit registers?
And is there a base registers as well?
Oh, sorry, yeah. Range and limit are the same one, base is the other one. So base is the first one, and the other one's called range, or it's called limit. Now, in this case, so in our browser example, when we first ran the browser and it was processed